with Nick, Marvin Kühnemann, and Mirza, and Nick and Marvin are here today. Mirza is. All right, so to start off, let's first maybe remember the K-clique and the K-hyperclique problem. So the K-clique detection problem basically asks for given a graph for a set of K vertices such that every tuple is connected by an edge. So, for example, here would be an easy 4-clique to see. And well, the general fine grid conjecture is that we cannot find cliques in time faster than n to the omega k thirds. Also for K-pattern graphs. And now, if you want to extend this problem to hypergraphs, so we're going from edges that contain 2 vertices to, in our case, 3 uniform hypergraphs, which is mostly the focus for this talk. So I'm basically only going to be talking about 3 uniform hypergraphs. Means that an edge contains 3 vertices, and a clique is now a clique if every 3 tuple of that set of vertices is connected by an edge. So this, for example, would be a 4-clique for hyperclique. And in that case, the hyperclique conjecture does no longer really allow for algebraic techniques, or at least they're not there are no algorithms found yet. So there is the conjecture that we can in fact not solve hyperclique detection in 3 uniform hypergraphs in time faster than n to the k, which also holds for K-pattern 3 uniform hypergraphs. And now the question that we're going to ask for this talk is, can we find cliques in regular graphs easier? So if I have a degree regular graph, so every vertex has, for example, degree d, is there any way to exploit this to, well, achieve an algorithm that finds cliques faster? And the answer is no, sadly. So it has been shown like 20 years back in the FPT community that K-clique detection in D-regular graphs is in fact FPT equivalent to K-clique detection in general graphs. And yeah, so I guess that maybe it's kind of like intuitive that this does not help, but this is kind of a nice result in that sense that we can now assume that finding K-cliques in regular graphs is hard as well, which, for example, lends some help for some reductions. For example, relatively straightforward reduction then would be that a D-regular graph G has a K-clique if and only if G has a K and K cut with some fixed amount of edges. So here a K n minus K cut is basically a cut where we consider the size of the vertex partition cut. And to maybe see this a bit easier, here's a small example. We have a 2 regular graph with 7 vertices, and we're checking for K3, so for triangles. And yeah, you can kind of see that in this case, the cut value we're looking for is exactly 0. And in the case that we have a 0 cut, we see that, okay, this is a triangle. And if we have a higher cut, this kind of means that there can be less edges connecting the set of vertices. So that's the general gist. So this this equivalency between the regular and non-regular problem kind of makes it easier to find reduction, which is kind of cool. And on the other hand, there's also been some progress on using regular structure for improved algorithms. So there was a paper that applied the hypergraph container method to gain improved algorithms for graph products on almost regular graphs. And now we want to answer the question, okay, is this also the case for hypergraphs? So is it easier in hypergraphs to find hypercliques if they're regular or not? And if so, how can we prove it that it's not easier as in the case for cliques? And for that, maybe there's another question that you might pose now is, how exactly does a regular hypergraph look like? So yeah, let's deal with that first. So our notion of regular 3 uniform hypergraphs are now no longer concerned with the degree of the single vertex. We want a slightly stronger notion, which is also mostly motivated for application, which I'm not sure we're gonna get to, but just bear with me then for that one. We instead want every pair of vertices to be somewhat regular. That means any pair of vertices, U and V, appear in the same number of edges. And for all case, we will also shift the setting a bit. We will shift this to the K-pattern setting. So either U and V are in different partitions of the graph and thus will appear in, let's say, if the graph, we call it gamma regular, appear in gamma regular edges together if they're in different partitions, but if they're in the same partition, they basically appear in no edges together. And the idea behind that is also that it somewhat generalizes nicely. So for H uniform hypergraphs, you would now no longer consider the pairs, but for example, the H-1 tuples be regular, which is kind of cool because then if the H-1 tuples are regular, then also the H-2 and so on tuples are regular. All right, so that's our general setting. And during working on this, we kind of noticed that there's been a lot of research done in the combinatorial part of mathematics, which are combinatorial block designs, which are kind of similar to this one. So there's like combinatorial block designs for more precisely triple systems and group divisible designs, which kind of have the same thing that we want. You have a set of points, and then you have blocks, or rather edges, which are in this case for triple systems, triples, and then you want that every pair of vertices is contained in the same number of blocks. And it turns out that it's not necessarily trivial to construct those things. And maybe I can give you a small intuition as to why this is hard. So for a general graph, let's just have like some small like cutout here. You can see there's like some vertices with degree 4, and there's some vertices with like degree 3. And if we just want to fix the degree for those vertices, we can just introduce a dummy vertex and connect it. Now, okay, this might produce cliques or anything else, but in general, this does not affect the regularity of any other vertices that we did not touch. But like for in this case, even very small sample of the hypergraph, we see that those two vertices are not in an edge together. So if you now want to have a higher pair regularity, then this would mean we would in some sense need to connect them. But as soon as we add any kind of dummy vertex, now they will share an edge, but this dummy vertex now will miss an edge with every other. So it's very hard to kind of make a hypergraph regular with any kind of local approach. So we need some kind of global approach. And this global approach in our case is basically a two-step program. So what we are trying to do to show a final result depends on two steps, which we'll get to later. But basically, what we get to is that the H uniform K hyperclique conjecture is equivalent to the H uniform regular K hyperclique conjecture in the K partite setting. So that for any H, the K H hyperclique problem, so the K hyperclique problem, the H uniform graphs, is solvable in time for some function f to the k times n to the g of k on K partite H uniform graphs, if and only if it is also solvable in some function f prime of k times n to the g of k on regular K partite part. And here regular is the strongest notion of regular we just talked about. Okay, and how did we approach this? Our first step is basically introducing some kind of special graph product that more or less gives us the properties that we want. So the first property that we want is that after this, apply this graph product with some other graph for a given graph G, we want that every pair appears on exactly lambda edges, so the graph is regular in the end, and it contains a K-clique if and only if the original graph that we used for the product also contains a K-clique, or in this case, we're rather talking about the hyperclique. So, for this, let's introduce the sign product, here denoted by O+ in our circle, of some graphs G and H. And this is kind of asymmetric because G can be an arbitrary hypergraph and H is a signed graph. So basically just a hypergraph that has a coloring function, coloring edges either positive or negative. And in this case, we'll just denote the positive edges by E to plus and the negative edges by E minus. And now the vertex set of this product is, well, just a cross product of the vertices of the original graphs. And now the edges that we construct will look the following way. So basically we have a reduction rule depending on whether an edge is positive or negative. If an edge is positive, then we add the edge U1, T1, U2, T2, U3, T3 to our product graph, if and only if U1, U2, U3 is also an edge in G. And conversely, if our edge is negative, we will only do this if U1, U2, U3 is not an edge in G. So if I can kind of give intuition, maybe it helps, maybe not. The idea is basically that we're doing the tensor product of G when we're kind of considering the positive edges, and we're doing the product with like the complement graph of G if we're considering negative edges. And maybe one thing that's also notable here still is that those U1, U2, U3 are not necessarily distinct. So for example, if I have some negative edge T1, T2, T3, then we can also connect to, for example, U1, T1, U1, T2, and U1, T3, which I hope I can show you in some small example. So this works in general for any kind of uniform hypergraph, and in fact, you can also apply to two uniform hypergraphs, which in fact are just simple graphs, like two uniform normal graphs. And in this case, I hope there's a small example that we can work through, which is we have like the for cycle and the pre-cycle. And yeah, the triangle is for a signed hypergraph. It has one positive edge, two negative edges. And if you consider the product graph now, what we do is, okay, we consider for the first vertex, 1A, we have a positive edge from A to B, and we have a edge in G from 1 to 2. So we add a new edge from 1A to B, from 1A to B. And the same goes for the edge 1, 3 with a positive edge. So those are the edges that we add that way. And now for the negative edge, for example, from A to C, we add the edge exactly if there's no such edge. So more or less, if we consider all edges that are not present in our original graph, then we will add an edge in the product graph. And this counts for the edge 1, 4, but also for the loop edge. So in the case of three uniform graphs, for example, for any kind of like degenerate edge that, for example, contains only two vertices. Okay. So that's a general approach that we use for the signed product, and now we want to have those two properties that we talked about earlier. The first one is our regularity property, and what we want is that if our signed hypergraph H is gamma regular, so any kind of vertices appears, any two vertices appear in gamma many edges, and in this case it's important that they appear in like gamma many positive edges and gamma many negative edges. Then the resulting graph of the product is the size of the original graph times gamma regular. And to see this, we're just gonna have a look at like two fixed vertices, U1, T1 and U2, T2. And let's consider on the left side down that the original graph G, so U1 and U2 are maybe like connected to UJ, UL, and UI. So in total, they have degree U1 and U2 many edges. And then on the other hand, they will obviously have the size of the graph minus degree U1 and U2 many non-edges. And if we now, for example, have a regularity of 1 in our graph H, that means we have one positive edge for two vertices and one negative edge. This basically means that there are, for example, well, the original edges of the graph in our product graph. So we get an edge to UJ T3, UL T3, and UJ T3 if we have a positive edge T3. And on the other hand, for every non-edge that was in the original graph, we get the negative degree of T1, T2 times the amount of non-edges. And if we now like consider this, then we can see easily that this kind of adds up, like no matter what degree the original vertices U1 and U2 had. If we like multiply this out, we see that in the end, the degree of those two new vertices, U1, T1, and U2, T2, are indeed size of G times gamma regular. So that's nice. That means that's a property that we need for like sort of graph H. If it is gamma regular, then after the product with any graph, the new resulting graph will also be gamma regular. Okay, and then for the second property, which I suppose is the most important for actually showing the equivalency of K-clique detection, is, and that's now an assumption that we need to make, if H contains positive K-cliques but no K-cliques containing a negative edge, we can show that the product G prime contains a K-clique if and only if G. So what do we mean by H contains only positive K-cliques? That basically means that any K-clique that I look at contains only positive edges and no negative, like there's no clique containing any negative edge at all. Okay, so how can we see this? Well, let's assume there's a clique V1 to VK in G. Then we also know that just by assumption, H also contains a positive K-clique. So basically, just by the definition of our product, the combined vertices will also form a clique in our product graph, right? And in fact, also all permutation in that case. So that's good. If our original graph has a clique, then also G prime will have a clique. Now, on the other hand, what if G prime has a clique? Well, then we know also by how we constructed the signed product that in fact the vertices T1 to Tk also need to form a K-clique in H. And by assumption, that K-clique needs to be fully positive. And well, if that K-clique was fully positive, then we also know that V1 VK is a K-clique in G, as we only add the edge VI Ti, VJ Tj, VL TL, if in fact vi, vj, vl is an edge in G, because that's the production rule for the positive hyper edges in this product. Okay, so that's basically the two properties, and both of these properties in the side product kind of like need a special kind of edge, so some special kind of graph. And well, now the question is, how does this edge look like? Like, can we actually construct it, and if so, how? That's the second step, is constructing such a, we call it template graph H. And here, for example, you can see some kind of two uniform graph that would fulfill those properties, right? We have like positive triangles, but no triangle containing a negative edge. And we see that every vertex is like too regular for the negative edges and too regular for the positive edges. And those are the properties that we want to have. And also, first of all, the graph needs to be signed, negative or positive. The graph needs to be regular, so every curve vertices appears in exactly gamma many positive and negative edges. Then for the second part, the Clique condition, we need that in fact the graph contains only positive K-cliques and no K-clique containing a negative edge. And then lastly, which is also rather important, we don't want our product to blow up, obviously, so that we can actually show fine range bounds. That means we want the graph that we construct to be rather small, so that our product in the end is also like only linear in the size of the original graph. And how do we proceed there? Well, for this we take K copies as our partitions of the graph of the group Z3 as K over 3-dimensional vectors, right? So we will more or less index the dimensions by triples. So if you consider some element in there, then 0, 0, 0 will be the first entry of the vector, and k, k, k is the last. And so I guess we fulfilled the first property. This is rather small, right? This is only dependent on k, so that's nice. And now we'll talk about how we construct edges in such a template graph. And for this, consider the k partitions of this graph, right? And we will add a positive edge if and only if the elements, we will only add edges between different partitions because we're talking about the k vertex settings. We will only add an edge between, in this case, elements x1, y2, and zk minus 1 from the corresponding partitions if those elements add up in the group, add up to 0, right? So, for example, here's a small example. We have, for example, the element 1, 2, and then zeros, 1, 1, then zeros, and 1, 0, 2, and then zeros. Those three elements add up to the all-zero vector. So exactly that means that we will construct a positive edges between those vertices. And right, so that's how we do the positive edges. And you might notice that if we pick two vertices, then in the group it is uniquely determined what the third vertex will be, and there's also only one, right? So if you just like move it around here, then x1 plus y2 will always result in some element minus zj in some other partition. So in particular, this means that if I fix some pair, for example, in this case x1 and x2, then they only form positive edges with every minus zj from every other partition, which are exactly k minus 2 other partitions. So any pair of vertices that we fix in different partitions will appear in exactly k minus 2 edges, positive edges together. So that's kind of nice. That means we have kind of constructed the first part, right? We have positively signed edges and they're somewhat regular. They are parallel. As for the negative edges, we will do basically the same thing, but now the edges should no longer, the vertices should no longer add up to 0, but instead to the unit vector of dimension 1, 2, and k minus 1 if we are taking vertices from the respective partition. So in this case, for example, we have that those three elements would to add up to the vector you can see here. And if we consider the negative edge going to be k, then obviously we need to have a different vector there. And the general idea that we have for regularity here is the same. So if we consider two elements, then there's also a uniquely determined element for every j that is the third vertex in the edge. Now you might notice that since we have this unit vector in there, this means that now the elements that we connect two fixed vertices to differs depending on what partition I choose, right? But nevertheless, still for two fixed vertices will end up with exactly k minus 2 edges that those two vertices share. So we also have fixed like the negative part of the edges, and they are also regular, chemistry regular. And now comes the last part of the construction. We need to show the template graph contains a positive K-clique, and in this case, it's rather easy, I hope to see, that any set where we choose every vertex corresponding to the same element. So for example, let's say xi corresponds to the element x. So for example, the all ones vector in every partition. And then we can see that since every xi corresponds to the element x in a group, then every triple of those vertices will have an edge, because we will always end up with 3x, which 1, 3 is 0 again. So for those sets, we always will get a K-clique. So that's kind of nice, right? So no matter which triple I look at here, they will always be connected positive edge. So that's good. And yeah, we see that the K-clique exists, and even several K-cliques exist. And now for a bit more interesting part is we need to prove that there are in fact no K-cliques that also contain a negative edge. And we will show an even stronger statement, which is that the template graph contains no 4 hyperclique with negative edge. So even no 4 hyperclique with negative edge exists, no matter what K we have. So for this, consider some 4 clique, in this case, maybe in the first 4 partitions, consisting of like elements W, X, Y, and Z. And now let's just assume, for example, that X, Y, Z is a negative edge. So this would then correspond to the fact that X, Y, and Z, the corresponding elements, would need to add up to the unit vector with the one in dimension 2, 3, and 4. Okay, so that's basically also possible to write in the sense that those 3 vectors have a 1 in the corresponding dimension. And if we now take a look at the other edges, for example, then no matter what edge we look at, for example, if it's a positive edge, then we definitely know that this dimension will also add up to 0, right? But even for negative edges, it is the case that if this edge is negative, since it is between different partitions, it has a different unit vector that we expect for example there. So that means that it will also be 0 in that corresponding dimension. So if we then now take a look at this and just make a system of linear equations and sum it up, we kind of see, okay, basically every vertex here appears 3 times, and we have 1, 0, and 1, 1, and 3 zeros. And if we consider this mod 3 again, then this is not possible because everything appears twice. So our assumption was false, and there is in fact no 4 hyperclique containing a negative edge. And yeah, that's kind of neat, because now we can use this approach to, for any given graph G, now compute a regular graph and now we do the following. We first compute some template graph depending on K. So if you want to solve K-clique for some graph K, then we just compute the corresponding template graph. It will have exactly K minus 2 regularity for positive and negative edges, and contains only positive K-cliques, and it is also of size only dependent on K. Then afterwards, we will just construct sign product with those 2 graphs, and we see that now in G prime, every pair of vertices in the K-partition setting appears in exactly K minus 2 times size of the original graph, many edges. And we also know that since edge of K contains only positive K-cliques with no negative edge appearing, we know that G prime contains a K-clique if and only if G contains a K-clique. And lastly, also the graph does not go up in any sense because we only have a size increase dependent on K. Okay, so that's basically the way that how we can give any hypergraph, make it regular, and if we then find a clique in the regular graph, we will also have the technical in the original graph. And yeah, actually I will have a bit more time, but I guess it won't really suffice to go in our applications of Max CSP. So I'm just gonna head on to concluding a bit. So in general, we had a look at this technique for 3 uniform hypergraphs, but in fact, this generalizes to any uniformity of hypergraphs. So our product does, I think you can see that easily generalized to H uniform hypergraphs, and also our construction generalizes easily to H uniform hypergraphs. And that means we can also extend it that way, which is kind of cool. The one problem that kind of persists is that just by the definition of the signed product, we will always receive a k-partite graph in the end, right? So now the question is there some way to maybe adapt this technique to, in the end, achieve a non-k-partite graph? And well, there could be two approaches. The first one would to find some way to maybe offer a product to allow for this, or the second one would be, well, we just basically need one ingredient, which is that the groups, so the partitions themselves, basically connect the vertices regularly, like in a regular manner, such that every two vertices in the partition are also like lambda regular, but does not introduce a clique. So this would basically boil down to finding some kind of way to, given any set of vertices, connect them to a regular hypergraph that is clique-free, clique-free. So that would be one approach to lift this result to non-k-partite graph, which would be cool. And then the question that also you could ask further is this result useful for other applications? So we used it for max CSP to show that in fact max CSP, depending on some kind of degree notion of a function, is in fact hard. So could this be useful for other applications? Would be very interesting to find something there. And then also another question that you could ask that we did not work yet on is, does this approach also extend to other subgraphs? So for example, could I also use this for, I don't know, maybe regularizing cycle finding? All right, then I guess I'm still a bit under time, but thank you very much for your attention. And if you have any questions, please shoot away.